Okay, so I assume we can start now. Hello, everyone, and welcome to the sixth session from the research track of ICPM 2020. The theme of this session is about rule mining. In this session, we have three papers to be presented, and starting with the first paper, which is titled A Temporal Logic-Based Measurement Framework for Process Mining. It will be presented by Alessio Cicconi. So please, Alessio, share your screen and start your presentation, please.
Okay, I'm sharing my screen. Tell me when you can see something.
Yeah, I have it. Good.
Okay.
Yeah.
Okay, you can hear me, you can see me, so I think we can start. So welcome everyone to this presentation. I'm Alessio Cicconi from the Vienna University of Economics and Business. And on behalf of all my co-authors, I hereby presenting you our temporal logic-based measurement framework for process mining. To do so, let me introduce you to my friend Mario. Now, he always would like to save his princess, right? But he usually ends up in this situation, where the little toad tell at the end of the castle, sorry, but the princess is not here. So Mario is a bit sad about that, about fighting and running, but then not getting his prize. And so at least he asked, okay, how do you know this? And Todd said, okay, actually I record all the games of the previous player passing through here. So Mario think, okay, maybe you are not the princess, but you may be useful source of information to reach her. So he asked a question like, okay, given your data, did the previous player complete the next castle? And the answer is no. Okay, so at least anyone did? And the answer is yes. So this Boolean answer is not really informative in this situation. He would like to know more. So Mario refined this question and asked, okay, how likely it is to complete a castle? And so now Todd thinks about it and said, okay, look, the first castle is quite easy, the second one is a bit more complex, and the last one is a mess. So it is really more detailed, but it is just one single perspective, the likelihood of the answer. So Mario asked if he can know a little bit more to plan the attack to the final castle. So Todd said, okay, you already know about the likelihood, what else I can tell you? I don't know, for example, the confidence of my answer, or I can tell you how much specific it is, your question with respect to the specific castle, or how much jumps you need for that level, or to not talk about the mushrooms that you're going to find according to your question. So very more a broad perspective, different perspective given the question, but yet it is still just for the specific castle, right? So Mario would like to know also more in general for how much it's gonna take to complete the entire game. So Todd can take his previous result and can gain some information like, okay, so the average of the likelihood to complete a castle would be, I don't know, 44% of the time, and so on and so forth for all the other measures. So now Mario has all the information that he needs, and he proceeds to the next castle, but no, wait, he was forgetting. So he also interested in defeating the boss, so he asked another question, a different one, more detailed, like, okay, if I'm tiny and not giant right now, and I'm going to find Bowser, will I die? Will it be a game over? And so he can answer also other kind of questions. So not just answering if the princess is or is not in a specific castle, but also different one. So, and now Mario is really ready to plan his attack to the castle of the boss. Now, you may have noticed that in the process of saving the princess and having all the event logs of the previous player to gain information, Mario never asked for specific action to, like, I had to jump here, then I have to run and then dash, specific sequence of actions, but he just was concerned about properties. He can deal by its own with the details then. So here we are into the declarative process mining world. And all the question of Mario could be encoded into declarative rules, either maybe through pure temporal logic or through user-level languages like declare. But the problem with current declarative process mining techniques is that when it comes to evaluate a formula, a rule, the limit is that either they support only a specific set of rules, so not a generic one, for example, only the declare standard template set, or they support just specific measure, for example, only support and confidence, or they just stick to one level of granularity, for example, just the result at the level of the entire log. So that's why we are here by proposing to you this measurement framework to evaluate declarative rules on event logs, which is capable of supporting any temporal rule, measure, and different level of granularity. Now, to start with a brief overview about the input and output of this framework. So in input, we will have that given a declarative rules and an event log and a set of measures. So mind that the measures are in input and it's not encoded into the framework. We are going to retrieve a specific evaluation of the rules in each event of the event log. Then we are going to have an extensive measurement for each trace, and then an aggregated view at the level of the entire event log. So let's dive into this box. First of all, the rules that we are considering here are specifically reactive constraints. So constraints were put into the form of if an activator condition arises, then I expect that also a target condition must hold as well. Now, the important things here is that the activator, so what triggers the interestingness of the trace is encoded into the logic. So it's not given then post hoc. And that any rule could be implicitly or explicitly reduced to this kind of pattern. And here in this work, extending on our previous one of BPM 18, we allow the activator and the target condition to be any temporal formula. So not just single event occurrences. And we are going to use linear temporal logic over finite trace for the definition of this formula. So in this way, we can define formula like, okay, if we start the trace or the castle, eventually I expect to end the castle till something more complex, like, I don't know, the last one, if I'm underground of the level, on the underground of the level, so for example, if I went previously from where I'm now below the ground and then I eventually emerged, then I expect not to be blocked at this moment, or eventually I fly away to unblock myself. For example, if we stick to this last example and we just shorten it for simplicity, and just a quick remark, this is not something that could be modeled with standard declare. How do we evaluate reactive constraint? Now, the difference with respect to classic LTL checking is that, first of all, the activator and the target condition are evaluated separately and independently. And both of them are evaluated in each event of the log, and also each event is computed, checked independently from the other events. For example, in the first event of the trace, in E, the activator condition is false because there is not a B before that point. While instead the target condition is true because E is different from C. So if we use 0 for false and 1 for true, and we can apply this in the same reasoning for all the other events. And we have a very detailed evaluation for each single event, which tells us not only when it is actively violated or satisfied the constraint in the trace, but also it tells us what happens when it is not active. And we'll see shortly why it is important to distinguish it. And that's our event level result. Now, you may recognize that support and confidence are one of the most used trace measures for declarative rules. Actually, they came from the association rule mining literature, where they were defined for rules like, if I have A in a set, then I expect B to be in the set as well. And they were defined over probabilities in sets. But actually, in the literature of association rule mining are present tons more of rules that are not really exploited in declarative process mining, because only 4 of them I could find to be used up till now. So is it not a pity that, I mean, there are all these measure availables that goes beyond the limits of a more simpler rule, or simply look at different perspective of the formulae? So what's my idea? So the measurement, those measures were defined for if identity rules, which are the exact same idea of reactive constraint like our example before. But because those measures are defined for probabilities, what is the probability of, for example, previously B or and eventually E over a trace? So the answer, given the detailed evaluation that he had before, we can extract a frequentist probability interpretation of the formulas, where we define the probability of a formula, for example, of the probability of the activator as the ratio of event in which the formula is fulfilled over the total number of events. So for example, in 6 events out of 9, the activator was true regardless of the target. And in the same way, we can devise the probability of the combination of the activator and the target. Now, given only this result, we can apply all the previous measurements as they are. So without tweaking or hard coding anything into the code. And that's also an important thing. We are not proposing those measures. We are supporting through our framework also those measures, because every probabilistic measure so defined is supported by default, by design, by our framework. And that's our trace level result. Now, of course, we did it for one single trace. We retrieve all the measure for one constraint. We can retrieve the same measures also for the other traces. So at that point, to have an overview, we can not only average each measure over all the traces in the log, but we can take all the information of the statistical distribution of those measures to have a more detailed view of what's going on. So now, that's basically our framework, up till the aggregation level of the event log. And we'd like to remark, to recap, that we add an input any reactive constraint, not any specific template set. We can support any probabilistic measure, and the result is from a very fine-grained level of the single event evaluation. We have tons of measures for the trace, and then we can aggregate at the level of the entire log. We implemented this framework into a proof of concept software, and we to check the performances, which are computationally linearly dependent on the numbers of rules and the number of events to check, and also in which support our theoretical computational cost, which we devised in the paper. And also in the real life logs, the time is quite reasonable. Find in the paper also the other data sets that we use to check. But why should we need so many measures, right? So let's make an example. I'm in a phone call or in a virtual conference, and there is some noise in the background. For example, you probably are hearing my fan, the fan of my computer, which is spinning crazy, but you don't care too much because you can still understand what I said. Instead, if you have some noise in front of the camera right now, in front of the microphone, you start to be instead annoyed because you cannot understand me. So you would like a measure, for example, to the increase of when the noise increase, to not just decrease, because you would like a measure to be resilient to this error up till the point in which nothing is understandable. Instead, if you're listening to a concert of the Vienna Philharmonic Orchestra, you don't want, and there is some noise, you don't want just that the measure goes down, but as soon as noise arises, you would like the measure to drop down because
you have 1 minute.
Any noise. Yes.
1 minute.
So in one case, we would like resilience for the measure. In the other case, we would like to be sensitive. And we for sure don't want a measure which do not realize there is noise at all. So depending on the context and depending on the rule, we need different measure. We also experiment this, and you can find the details in the paper. So the limits is that we are considering only the control flow perspective, and the measure are only for single rules and not for the entire model. And for future outlook, we would really like to give all this new data, instead of overwhelming a user with tons of measure, to give it instead to a machine learning techniques who like to crunch a lot of data. But instead for user, it would require to devise a method to select or combine the best measure, depending on the context. And that said, I would like to thank you for your attention and welcome any of your inputs.
So thank you, Alessio. So for the audience, please, you can use the question and answer or raise your hands. And we already have one question from Ingo. So maybe I give Ingo the chance to ask his question live. So Ingo, please, you can now talk. Ingo. Okay, so maybe then until he's able to talk, I can speak his question. So his question is, you keep saying probability, but doesn't that make assumptions about the predictive power, which in general you cannot make?
Can you hear me now?
Yes, yes, we
okay,
can now. So please repeat your question, maybe better than me.
Sure, yeah. So I just wrote a short version of the question into the Q&A. So you keep talking about likelihood and probability, right? But let's look at, your example of Mario, but you kept saying it afterwards as well. And first of all, thanks for a very good talk. I think this is an interesting approach, but just on the terminology, it seems this is actually coming also from, the older rule literature you were talking about. So if I'm playing Mario, right, maybe I'm a super gifted player and my chance of actually finishing the game is 100%, right? But you kept talking about likelihood and probability. So what I'm trying to say is, you don't know everything about the Mario in front of you because there is a human player behind him. And so this is just symbolic for the world in general. The data doesn't express everything that is happening in the world in many, many cases. And so by talking about probability and likelihood, essentially we make two assumptions. One is that we have enough contextual knowledge to make actually a good prediction. And the other one is that past data is actually able to predict the future, which may or may not be the case. Right? And that's why I'm saying in general, it doesn't strike me as a question of probability. It's more a question of relative frequency.
Mm-hmm. Yeah, thanks for your input. Probably maybe a bit too relaxed in the presentation with the terminology. Yes, indeed, we are not talking here about prediction and probabilities based, yes, only on previous data, not on any expectation of later on. And the probability is defined over a frequentist, as you also mentioned, on a frequentist base.
But it sounded like the classical rule literature was using also the terminology of probability and likelihood.
Yeah, exactly. But that's what we did here. We breached toward, I mean, a while before we just pick just few measures for the declarative rules and we apply them in our own way. Now instead, it's like, okay, we had this intersection between those literature, so let's draw everything from them in such a way that we can apply it here.
Yeah. No, it does make sense. It just like that part of the terminology that I'm convinced about.
Yeah, probably. Thank you.
Okay.
We'll rephrase it in the future.
Okay, so thank you, Licio, for your presentation. And now we can move to the next paper. So the next paper is called Rule Mining in RUM. It is presented by Antti Alman. And the paper is co-authored together with Alexander Nolte, Claude De Ciccio, Dominic Haas, and Fabrizio Maria Maggi. So Antti, please share your screen and the floor is yours.
Okay, just give me a moment. Okay,
Sure.
Now you should see the screen.
Yes, we can.
Okay, so my name is Antti Alman. I am a PhD student in the University of Tartu, and I will be presenting the paper Rule Mining with RUM. This paper is written in collaboration with Claudio De Ciccio from La Sapienza University of Rome, Dominic Haas from the Vienna University of Economics and Business, Fabrizio Maria Maggi from the Free University of Bolzano, and Alexander Nolte from the University of Tartu. The purpose of this paper is to introduce a novel rule mining application RUM that is based on the declarative process modeling language Declare. This presentation will be in some respects less technical than usual, since we intend RUM to be suitable for users who are not experts of the Declare language. The motivation for developing RUM was perfectly summarized by one of the research challenges outlined in a paper by Dice Lutz. The challenge reads: the further development and industrial adaptation of Declare technologies would greatly benefit from an extensive, actively maintained toolset. And this is exactly what we aim to achieve with the introduction of RUM. But before giving an overview of RUM itself, it is important that I introduce the main concepts of the Declare language, and I will aim to do this in less than 2 minutes. So, one way to understand Declare is to think of it as a language for describing a process as a set of business rules. An example of such a rule could be: the process starts with the activity ER registration, and this simple rule can be represented in the Declare notation as shown on the right. Of course, there can be multiple rules describing the process. For example, we could add a rule: if ER registration occurs, then IV antibiotics occurs afterwards. It is also possible to enhance the rules by addition of data conditions. For example, we could say that the rule we just added applies only if the attribute CIRS criteria 2 or more of the event ER registration is true. And we can continue adding similar rules to the model until all the important aspects of the process have been described. Finally, there is one very important aspect of Declare and declarative languages in general that needs to be mentioned, and that is the open world assumption, which means that if an event does not conflict with the model, then it is allowed. The main implication of this assumption is that a Declare model is not expected to define all possible execution paths of a process, but instead the focus is on defining the rules that hold true for the process as a whole. Now that we have covered the basics of Declare, we can move on to discussing RUM itself. The name RUM comes from the term rule mining, which is also the main focus of the application. RUM can also be described as a toolset for declarative process mining, which contains various methods for process discovery, conformance checking, editing Declare models, log generation, and monitoring. And one of the main characteristics that we emphasized during the development was ease of use, with the goal being that users not familiar with Declare would be able to use the application effectively. In this diagram, you can see all the main sections of RUM and how they interact with the event logs and Declare models. Each section corresponds to one of the functionalities provided by RUM and consists of different methods that can be used for implementing that functionality. I will give a short introduction to each of these sections in the upcoming slides. The discovery section allows the user to open an event log and to use different methods in order to discover the Declare model from the log. There are 4 methods available for process discovery: Declare miner, minerful, MP-declare miner, and MP-minerful. The MP variants use the same base mining algorithm that is implied by the name, but with an added post-processing step that aims to discover data conditions from the event log. The figure on the current slide displays the declare view of the discovered model using the standard declare notation. However, there are 2 other views available. One of these is the textual view. This view gives a description of the model using simple natural language sentences that aim to describe the meaning of each constraint. For example, in 100% of traces in the log, IV antibiotics occurs exactly once. The second one is the automaton view, which displays the discovered process model as a finite state machine. This view is meant for people who are either familiar with the formal semantics of declare or with automatons in general. The conformance checking section allows the user to open a model and an event log in order to compare them. There are 3 methods available for conformance checking: declare analyzer, declare replayer, and data-aware declare replayer. From the user's perspective, there are some important differences between these methods. The declare analyzer reports constraint activations, violations, and fulfillments. In contrast, the declare replayer and the data-aware declare replayer report trace alignments. Additionally, the data-aware declare replayer can detect if some data was missing or had wrong values. The MP-declare editor allows the user to open and modify an existing process model or to create an entirely new model. Editing the model is performed through the Activities and Attributes panel on the left and the Constraints table at the bottom. The visual representation of the model is updated on the fly during editing, and the same 3 model views are available as in the Discovery section: the declare notation, textual, and automaton. An alternative way to add constraints to the model is to use the chatbot Tekla, which can detect constraints from both natural language speech and text. The editor is fully MP-declare compliant, meaning that it is possible to define declare constraints enriched with time and data conditions. The log generation section allows the user to generate an artificial event log based on a declare model. This can be useful, for example, to gain an understanding of how a process might look based on a given model, or to generate datasets with certain characteristics that can be used for testing new algorithms in a controlled environment. There are 2 log generation methods available: alloy log generator and minerful log generator. The main difference between these methods from the user standpoint is that the alloy log generator is also able to account for data conditions in the input process model at the cost of lower efficiency. And the final section is the monitoring section, which allows the user to analyze how the states in the model change as each event in the event log occurs. There are 2 monitoring methods available: MP-declare with alloy, which is an alloy-based monitor based on MP-declare, and Mobucon LTL, which is one of the first state-of-the-art declare monitors. It is possible to both explore the states at a specific point in the event log or to let the events play out in an animation. For example, in here we can see the initial states that the model takes after the first event, ER registration, occurs, and how the states change after the second event, IV antibiotics, has also occurred. And when skipping to the final event, we can see that 2 of the rules defined in the model were violated by the end of the given trace. Next, I will describe the setup and findings of the user evaluation that was conducted together with writing this paper. The user evaluation was set up as a qualitative study, meaning that we focused on observational findings that identify design features easy or hard to use. The performance of the participants was not measured in quantitative terms, meaning that we did not track success rates, completion times, etc. The study had 8 participants, 4 of whom were BPM experts and 4 were declare experts. This split was intentional, as the application is intended to be usable for both groups. The study was conducted in 2 stages. First, practical sessions of using room, and then a survey about participants' perception of room. The application scored quite high in the survey. For example, good products are expected to have a score between high 70s to high 80s on the system usability scale, and the result for room fits well into this range. However, the score of 81 points also indicates that further improvements are possible, as truly superior products are expected to score over 90 points on the SUS scale. It is interesting to point out that the Declare experts scored the application lower than the BPM experts. One possible explanation may be that Declare experts are already used to the existing tools and the graphical notation of Declare, and therefore see the improvements in room as less impressive. However, the Declare experts are also more likely to continue using the application. One possible explanation may be that they need a toolkit that collects the Declare-based tools available in the literature. In practical sessions, we used the same list of tasks for all participants. The tasks were relatively simple, and the participants were given assistance in cases where they had difficulty. This was done to ensure that they were able to use all of the main parts of the application. During the tasks, we used a real-life event log that was slightly modified for the tests. Each practical session took between 45 minutes to 1 hour and was recorded. The recordings also included discussions and suggestions from the participants. In order to analyze the practical sessions, we reviewed all the recordings in depth. During the reviews, we noted down everything that seemed important about the usage of room. For example, if the participant paused before finding how to export the model, then this was noted down. This resulted in a total of 540 notes, which means 68 notes per participant on average. And these notes were then organized using a technique called affinity diagramming, which is basically a way of clustering similar notes together and finding relevant themes for the clusters. This resulted in 10 main clusters based mostly on functionality and 110 subclusters. And on this page, you can see the UI feedback subcluster from the general feedback cluster of the affinity diagram as an example of one of those clusters. In general, the application was well received. We got multiple positive comments about both the visuals and the layout of the application. Multiple participants also commented that such an application was needed. Some of the section-specific highlights would be that the meaning of each template should be described in the application. This relates mostly to the discovery and MP-Declare editor sections. In conformance checking, it was recommended to add some kind of global statistics to quickly evaluate how conformant the event log is to the model. And in the editor, it was interesting to note that roughly half of the participants wanted to use the visualization for editing, which is not possible in the current version of the tool, while others started immediately using the tables. To round up the presentation, I will give a few thoughts on our future plans. The most important of these is the continued development of room. Some of the possible future improvements are adding a visual editor and extending the list of supported constraints. Additionally, we intend to work on further polishing the user interface and fixing any bugs that may be detected by the process mining community, while also working toward integrating the feedback from the user evaluation. We are also exploring some options to perform new user evaluations with a larger set of participants and/or in industrial environments. And finally, Room is open source and freely available at the website rulemining.org. We invite everyone to give Room a go and see what information that you can gain from your favorite event logs. And of course, a big thank you for the participants of the user evaluation. That is all for my presentation. Thank you for your attention. And if you have any questions, feel free to ask.
Thank you, Antti, for the presentation and keeping the time. I see one participant, Ahmed Tailab, is raising his hand, so I will allow him to talk to ask his question.
Mm-hmm.
So please, Ahmed. Hello. Okay, so
I think he's muted at the moment.
Yeah, I'll ask him again to unmute, but yeah. Okay. So until yeah, are you ready? Ahmed. Okay, so maybe I can ask a question. So, so are you seeing room as like you envision it as the to play the role of pro-M, but maybe for declarative processes? Or
I wouldn't say it plays the role of PROM specifically, because PROM is in some sense, PROM is kind of like a larger application, which, I mean, its design goals, one of its design goals for PROM was to provide like a plugin architecture where anyone in the community could possibly come, do their implementation of whatever new algorithm they feel like doing, and make it available. In some sense, I would maybe compare Room more to the application named Disco, which is used for the procedural models. And why I would make that comparison is because Disco as well is kind of like the user-friendly process mining tool, in my opinion. If you use it, I mean, I have seen even system administrators who don't know anything about process mining, yet they can effectively use Disco because the user interface is just so well polished. And this is something that I would like to do with Room eventually. I don't think I'm quite there yet, but it's close.
Okay, and extensibility, is it on the plan somewhere?
Extensibility,
like, as you mentioned with the PROM, like you can add plugins to PROM or PROM, but are you planning something like this with Room?
Currently, Room does not have any plugin architecture or framework in it. So if I need to add new algorithms to there, then this would mean actually changing the core code of Room itself. However, it is the plugin or the algorithms themselves, they are quite well encapsulated in the code. So it wouldn't be too much of an effort to add something new in. But at the moment, we are not going in the direction where it is, of course, open source application. So you could come in and add your own things into it. But at the moment, we are not going in the direction of having like an extensive plugin framework and repositories like are available for PROM.
Okay, so thank you very much, Antti. If you may unshare your screen, and
yes.
And we now move to Zahra. So she will present her paper and about process mining meets causal machine learning, discovering causal rules from event logs. So please, Zahra, share your screen, and the floor is yours.
Thank you. Can you all see my screen?
Yeah.
Okay, great. Hello, everyone. Welcome to this presentation about the paper titled Process Mining Meets Causal Machine Learning, Discovering Causal Rules from Event Logs. My name is Zahra Dasht-Bozorgi. I'm a PhD student at the University of Melbourne. And this study was done in collaboration with Irena Tainema from Booking.com, Marlon Duma from the University of Tartu, and also Marcello La Rosa and Artem Poliviani, also from the University of Melbourne. So as we all know, business processes are a collection of events, activities, and decisions that lead to an outcome. Some outcomes add value to the company and their clients, and some of them don't. So naturally, organizations are always trying to improve their processes such that they have a higher rate of positive outcomes. So in this study, we discover recommendation rules that seek to increase the likelihood of achieving a positive outcome in a business process by performing an action on a subgroup of cases. We also estimate the causal effect of these actions on the subgroup and provide a cost-benefit model for applying the recommendations, which is based on the incremental ROI. So first, I'll talk about the preliminaries in causal inference, which is necessary for understanding our framework. Causal inference is mainly about inferring the effect of one thing on another thing. It can be the effect of any policy or intervention or treatment. For example, the effect of a treatment on a disease, or the effect of an action on the outcome of a business process, which is the focus of this study. Some notations that we use here are Y denoting the outcome, T denoting treatment assignment, and X denoting case attributes. And both Y and T are considered binary in the study. So how do we measure causal effects? We do it by taking the difference between potential outcomes. To see what that means, let's look at an example. Suppose we have a loan application process, and we want to know whether calling a customer after making him or her an offer has a causal effect on them selecting the offer. Now, suppose we have two hypothetical worlds. In world 1, all customers get a phone call after an offer is made to them, and in world 2, no one gets this phone call. So each process instance has two potential outcomes. One outcome in world 1 denoted by Y superscript 1, and another in world 2 denoted by Y superscript 0. To measure an average treatment effect, the average outcome of world 2 should be subtracted from the average outcome of world 1. But most of the time, an action or treatment has different effects on different cases. For example, making a phone call does not always cause a customer to select an offer. Maybe the offer is already really good and the customer would select it whether or not a phone call was made to them. So what we are really interested in is a subgroup of cases where an action has a high causal effect on the outcome. And this is measured by the conditional average treatment effect, or uplift, which is the expected difference in potential outcomes conditioned on a set of variables X. Inferring causal effects would be easy if we had both potential outcomes, but we have a fundamental problem here known as the fundamental problem of causal inference. The problem is that we don't have two worlds. We only have one, and we only get to observe one potential outcome. And in this table, you can see that either Y superscript 1 or Y superscript 0 is missing for all cases. So one way to deal with this problem is to conduct a randomized experiment, but most of the time experiments can be expensive, time-consuming, or even unethical. So the next best solution is to study observational data and infer causal effects from them. So event logs are a form of observational data. So the aim of the study is to first discover interventions or treatments that can potentially have a causal effect on the outcome, and then use causal machine learning to discover causal rules. This figure here shows the overview of our approach. It has three main steps. In the first step, candidate treatments are generated. Next, subgroups in the event log are discovered where the treatment has a high causal effect on the outcome, which leads to what we call causal rules. Once we have such rules, the third step is to rank the rules based on a cost-benefit model to determine applying which treatment has a high return on investment. So in the first step, the aim is to generate recommendations automatically. This is done using action rule mining. Action rules are an extension of classification rules. Instead of predicting the class label of a given case, it tells us what should be done to change the class label of a case. And in order to do that, attributes should be defined as either controllable or not controllable. This is done to avoid having action rules that are impossible to carry out. So this is the general form of an action rule. It says that if we have an uncontrollable attribute A, which has a value A1, and a controllable attribute B, if we change the value of B from B1 to B2, then the outcome will change from Y1 to Y2. To understand it better, let's consider the loan application process mentioned earlier. Suppose it has two attributes, long goal and number of payback terms or months. As input, we need to specify which one is controllable and which one isn't. And in this example, long goal is not controllable because the bank cannot tell the customer to change their long goal. But the bank can control the number of payback months, so it's considered controllable. The This is an example action rule, which states that if in applications where the long goal is home improvement, changing the number of terms from 48 to 84 months will increase the chance of the customer selecting the offer. And the support of this rule is 5%, which means that in 5% of cases, this treatment or action is correlated with this outcome. So why don't we stop here? We have a rule consisting of a precondition, an action, and an outcome, which was our goal in the beginning. This is because this rule is not causal. It can only tell us that a change in the number of terms is associated with a change in the outcome, but there is no causal relation captured here. So this is why we need the second step in the framework, causal rule discovery. We previously identified actions that are highly correlated with a positive outcome. Now we use causal inference to determine if they really cause the outcome to change or not. And to do that, we use uplift trees. Uplift tree algorithms discover subgroups in the log that have a high uplift or a causal effect of a given treatment. Here you can see the uplift tree that was constructed for the action rule mentioned in the previous slide. So the main difference between an uplift tree and a normal decision tree is the splitting criterion. The splitting criterion of the uplift tree is the difference in the distribution of the treatment and control groups before and after a split. So it is the gain and divergence after a split. 3 divergence metrics can be used, the Koback-Leibler divergence, Euclidean distance, and chi-square divergence. So basically, the splits try to maximize the uplift, and it is done by computing the difference in the average outcome in the treatment and control groups, conditional on some variables x. So recall that in the preliminaries, we said that uplift is calculated by taking the difference in potential outcomes conditional on x. But unfortunately, these 2 measures are not equal in observational studies. And the reason for that is confounding in observational data. Confounding is the presence of a variable that affects both treatment assignment and the outcome. When we have confounding in our data, it means that the group that receives the treatment is fundamentally different from the group that doesn't. And ideally, we want the treatment and control groups to be balanced, meaning that the distribution of variables in cases in both treatment and control groups should be similar. So how do we address confounding in uplift trees? The answer is normalization. The normalization value is calculated with this formula, and this factor punishes tests that split the control and treatment groups in different proportions, because such splits indicate that the treatment is not independent from the assignment of cases between the two groups. The unevenness of splitting proportions is measured using divergence between the distribution of the test outcomes in both control and treatment datasets. Tests that are dependent on group assignment will be punished by receiving a low weight. And finally, after normalization, the final splitting criterion is the gain divided by the normalizing value. So after applying the uplift tree algorithm, our rule looks more like this. The action and the objective are the same. What's different now is the precondition. This subgroup here, which is our precondition, shows cases where this action has a high uplift score. So the last step in our framework is to rank the rules based on a cost model. This is because it's not always profitable to carry out interventions with a negative incremental return on investment. So we incorporate the uplift measure in a cost-benefit model that corresponds to the incremental ROI. So using the expected causal effect or uplift of applying a treatment, the value of the desired outcome, and the cost of a treatment, we produce a cost-aware ranking of the rules. We calculate the net value of applying a rule, and the user may pick the rule that have a net value above some certain threshold. We tested our approach on the BPI Challenge 2017 log. So the best way to evaluate our recommendations is to do a randomized experiment. But since that was not possible to do for us, we compare our results with the reports of the winners of the BPI Challenge. So the log records cases of a loan application process. And as you can see, we classified the attributes in the log into controllable and uncontrollable. So application type, loan goal, etc., they are considered uncontrollable, and attributes like number of terms or monthly cost are considered controllable. We ran the action rule discovery algorithm on this dataset and discovered 17 distinct recommendations. And the uplift tree was constructed for each of the 17 recommendations, which resulted in 8 causal rules. And you can find the details of these rules in the paper. So overall, our recommendations are in line with the recommendations of the winners, but we go a bit beyond the findings of the winners and provide subgroups of cases for which a recommendation should be applied. For example, in the reports of the winners in the academic category, they recommend to increase the number of terms. We make this recommendation more detailed by saying how much it should be increased. For example, from 48 months to more than 120 months. And also we provide the subgroup for this recommendation, which in this case is customers with a credit score in a certain range and first withdrawal amounts less than 8,300. But sometimes our results were different from the results of the winners. For example, in the report of the professional category, they find that the duration of the process impacts the outcome negatively and it should be decreased. This did not emerge in our results, so we tried to find out why, and we found that the duration of a case is indeed correlated with a negative outcome, but we also found that most of the delays were because of the customers not responding to the bank's requests. So basically, these are cases where the customer is not serious about the loan application, and decreasing the duration from the bank side does not necessarily lead to a positive outcome. So for future work, we plan to adapt this approach for other types of recommendations. For example, instead of changing attribute values, recommendations could be in the form of skipping or reordering some activities. Also, other goals can be considered, such as reducing waiting times or reducing waste. Another avenue for future work is taking into account the effects of unobserved confounding. And lastly, we plan to strengthen the evaluation of this approach by conducting a randomized experiment or a case study with an organization. Thank you for your attention, and if you have any questions, I'll be happy to answer them.
So thank you, Zahra, for the presentation. I can see that Dirk has raised his hand, so now I'm allowing him to talk. So please, Dirk, unmute your mic.
Thank you, thank you, Zahra. Really nice presentation. I like it a lot. It's also very clear. Very nice work. I guess I have questions about, say, your last slide, right? So because everything else I think is very solid. So if we look at the BPI Challenge 2017 process, then one of the interesting things there is that offers can be sent at the same time or one after the other, as an example. So you can have sent 2 offers. Once they're sent in parallel, right? And once kind of you get the feedback from the customer and then you send another one. In terms of total number of offers, it's the same. But the order in which they come is very different, right? So there's a process feature, there's a behavioral feature in there that matters. And I mean, that's one of, say, these confounding effects, right? So you can see it there. And I think there's many other things that are happening inside that process. Yes. But of course, you capture with the control variables to look at. Yes. What I'm worried here, and that's my question is, that there could actually be so many confounding effects in the process, right? So because of the very complicated behavior that's going on. Also, there's concept drift in the process. The process changes halfway in the data. There's severe workload changes in the process. There's many, many things going on that if you try to put off all of them, the rules could become meaningless because you go to super tiny, say cause effect rules. So do we have any thoughts on this?
Yes, that's a very valid concern. So for future work, as I mentioned, one of our directions is to take into account the effects of unobserved confoundings. And this is, well, there are many ways to deal with that. For example, one method is sensitivity analysis. So what we do in sensitivity analysis is to not measure all the confounding variables, because of course that's not possible, but to analyze how sensitive our inference is to these confounding effects. So they might exist, but they might not change our conclusion, our inference. I'm not sure if I could get my meaning across to you, but
I get the idea. Yes. Yes.
So yeah, that's yeah, definitely for future work.
Okay. So the next question is from Will. Please, Will, ask your question.
So you can hear me?
Yes.
Yeah.
Okay, good. Yeah, so I would like to join Dirk in congratulating with, I think, an excellent presentation and something that is, let's say, a super interesting topic. Just like Dirk, I have, like what you did is clear and I think is very nice. I also have, like Dirk, questions about like what would be the next step. So for example, Marcus Days had a paper at BPM last year, and he investigated the effect of interventions, and he's working in a company, so he's able to not just predict that something is going to be good, but he can also actually, let's say, implement these changes and then do A/B testing to compare like what the effect of a certain intervention is. And that study, it was actually very difficult to get it accepted because the results were negative. And so what was predicted to be positive, in practice, you wanted to avoid the number of reclamations and it increased. So can you tell a bit about the plans or the setup that you have in mind to go to this next step and then actually test it in like a realistic situation?
Yes, that's definitely our plan. We don't have any data set or any definite plans yet on who to test this method with, but it's definitely there because that's the only way to rigorously validate our recommendations. But the method with observational data, at least it tells us which of the recommendations are more likely to be effective. So like in the action rule mining algorithm, we get many rules, especially if we lower the support threshold. But with the Uplift Tree, with causal inference, we can narrow down the rules that are more likely to be effective rules.
No, that's clear, but my point would be that I think in many situations you cannot do this type of work based on a data set.
Yes,
because
that's true.
You want to change reality, and in the data set you can never see like A/B testing, right? So
yes.
And of course you can do that using simulation, but then you have programmed basically what should be the outcome. That also doesn't help.
Yes,
but
yeah,
it's
that's
a super interesting topic. Yeah, thank you.
Yes, that's a very challenging part of the evaluation. Definitely, I agree.
Okay, so we still have room for one more question, and this is going to be from Eric. So please, Eric, unmute and ask your question.
Hi, can you hear me?
Hello, yes.
Yep.
Hi, great presentation, Zara.
Thank
this
you.
is kind of related to Will's question. So suppose that in the observational data, you observe a hospital process where sometimes you have 2 nurses, sometimes you have 3 nurses, but your machine learning model can extrapolate and say that the best thing to do would be to put 5 nurses. However, this is a situation you've never observed in the data. Is there a confidence score or a confidence interval that you can attach to the impact? And are you planning to integrate it into your approach?
Not in this approach, but in the extension of this paper that we're working on now, we're planning to incorporate confidence intervals for this. Yes.
Great, thank you.
Okay, so I think we have just skipped the time in a perfect way. So if there are no more questions, I would like to ask to thank the three speakers and thank you all the attendees for attending this session. And this now comes to a conclusion for this session, and I hope to see you in the upcoming 2 sessions of the conference. Have a good day then. Bye-bye.